Complex stress and strain. In this chapter, we will find out stress or strain on inclined planes because till now we found the stress only on cross-sectional plane. Because of normal load, only normal stress will come on cross-sectional plane. But because of same normal load, and shear both will come on inclined plane. For example, let's take only axial load P is applied. In this cross section, only sigma will be there, but in this cross section, P will be like this because of Pn will be like this, and there will be Pt component, tangential component, non-normal component. Due to that, both sigma and shear will be there. Transformation of stress from cross section to inclined plane for 1D stress. Consider a rectangular bar of thickness T. At this section, sigma will be in this direction. We will have only sigma at T. If on plane ABCD at an angle theta, sigma theta tau theta will be there. Consider wedge shape element for stress analysis. ABC. Theta is angle, sigma is here, sigma theta and tau theta on this wedge plane. BC by AC is equal to cos theta. By static equation, Fx prime is equal to 0. Sigma theta into AC into T is equal to sigma into BC into T into cos theta. In this direction, to balance sigma Fx prime, x prime, y prime is in this directions. Sigma theta is equal to sigma cos square theta. Sigma Fy prime is equal to 0. Tau theta into AC into T plus sigma into BC into T into sin theta is equal to 0. Tau theta is equal to minus sigma cos theta sin theta. Tau theta is equal to minus sigma by 2 sin 2 theta. For maximum normal stress, d sigma theta by d theta is equal to 0. Sigma into 2 cos theta into minus sin theta is equal to 0. Minus sigma sin 2 theta is equal to 0. 2 tau theta is equal to 0. Tau theta is equal to 0. On plane of maximum normal stress, shear stress must be 0. Must be 0. Principal plane. It is plane on which normal stress is maximum or shear stress is 0. In 2D diagram, two principal planes will be there, will be present, and they must be mutually perpendicular to each other. Principal stress. It is normal stress acting on principal plane. On two principal planes, two principal stresses are there, and they can be denoted as sigma 1 is equal to major principal stress, maximum normal stress, sigma 2 is equal to minimal principal stress, or minimum normal stress. Sign convention. Sign convention. Like if phase and direction both are positive, then it is positive. If both are negative also, then it is positive. If one is positive and one is negative, then it is negative. For example, x y, here both are positive, here both are positive, but here both are negative, so these are also positive. This is total positive. And another, if tries to pull outward, then it is positive. If tries to pull inward, then it is negative. Normal stress sigma x comma sigma y and shear stress tau xy is acting on two mutually perpendicular planes, and it is required to find expression of normal and shear stress on a plane which has inclination theta from vertical in anti-clockwise direction. Sigma okay, theta anti-clockwise rotated. By static equation, sigma theta similarly like as before, if we take sigma theta is equal to the static equilibrium, by static equilibrium we'll get sigma theta is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Tau theta is equal to minus of sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta. Resultant stress sigma r is equal to root of sigma theta square plus tau theta square. Sigma theta tau theta alpha. Alpha is equal to angle of obliquity. X, Y, theta rotated in anti-clockwise direction. Theta If theta is rotated in clockwise direction, then minus theta. Positive on x-axis or negative y direction. Find out the value of sigma y. Sigma x is equal to 8, tau x is equal to minus 3, and plus 45 degrees, sigma theta is equal to plus 2, tau theta is equal to minus 3. Okay, these are just workbook questions. And design of brittle materials, principal plane. D sigma theta by d theta is equal to 0 or tau theta is equal to 0. Theta tends to theta p. Sigma x minus sigma y by 2 sin 2 theta p plus tau xy cos 2 theta p is equal to 0. Tan 2 theta p is equal to 2 tau xy by sigma x minus sigma y. Theta p1 is equal to theta p 0 degrees to 90 degrees. Theta p2 is equal to theta p plus 90 degrees to 180 degrees. Principal stress, put theta p1 or theta p2 in equation 1. Sigma theta sigma 1 or sigma 2. Sigma 1 comma 2 is equal to sigma x plus sigma y by 2 plus or minus root of sigma x minus sigma y by 2 whole square plus tau xy whole square, plus for sigma 1 minus for sigma 2. Find out the value of sigma 1 and sigma 2. Tan 2 theta p is equal to 2 tau xy by sigma x minus sigma y. Theta p is equal to 40 degrees. Sigma 1 you can get it generally only. Find out length of major and minor axis of ellipse which generates after deformation of circle. Epsilon 1 is equal to sigma 1 by e minus mu sigma 2 by e. A dash b dash minus ab by ab is equal to, we'll get 1, and epsilon 2 also will get in the same way. From that we can get c dash d dash, that is what is length of major axis and length of minor axis. 650 Newton force applied at end C. Normal and shear stress at point D. Principal stress and corresponding plane at D. Given diameter of part AB. Basic loads at x cross section. The axial load is equal to, if we remove this and apply 60-50 Newton and torque, shield load is equal to 650 Newton, bending x-axis is 650 into 250, torque moment 650 into 450 is equal to 292.5 Newton meter. Stresses at point D, which is stress here. Stresses at point D. Sigma bending stress sigma is equal to m by z is equal to 32 m by pi d cube. After solving, we will get 61.3 MPa. Torsional shear stress tau is equal to T by Zp is equal to 16 T by pi d cube is equal to 55.17 MPa. Shear stress due to shear load tau is equal to 0. Y tau is equal to 0 at periphery. Shear stress is equal to 0. Yeah, due to that shear stress distribution, shear stress is 0. So finally sigma x is equal to 0, sigma y is equal to 61.3, tau xy is equal to tau x yx is equal to 55.17. At periphery tau is 0, that is a new concept and important one. Sigma 1 comma 2 is equal to sigma x plus sigma y by 2 plus or minus root of sigma x minus sigma y by 2 whole square plus tau xy square. So you can get sigma 1 and sigma 2. 2 and 2 theta p is equal to tan inverse 2 tau xy by sigma x minus sigma y. Yeah, okay. Another workbook question. Design of ductile materials. Maximum shear stress plane. D tau theta by d theta is equal to 0. Theta tends to theta s. Theta s1 is equal to theta s. Theta s2 is equal to theta s plus 90 degrees. Theta p. This is theta p1 plus 45 degrees. This is theta p2 plus 45 degrees. Maximum shear stress, put theta is equal to theta s1 or theta s2. Tau theta is equal to tau max. Tau max is equal to root of sigma x minus sigma y by 2 whole square plus tau xy square. This is in plane tau max. Sigma 1 is equal to a plus b. Sigma 2 is equal to a minus b. Mod of sigma 1 minus sigma 2 by 2 is equal to B is equal to tau max. For 3D stress, tau max absolute is equal to maximum of mod of sigma 1 minus sigma 2 by 2, comma mod of sigma 2 minus sigma 3 by 2, comma mod of sigma 3 minus sigma 1 by 2. And this is sigma 1 minus sigma 2 by 2 is in plane tau max. Rotation about z axis, rotation about x axis, this is rotation about y axis. These two are outplane tau max. For 2D stress, sigma 3 is equal to 0. Tau max is equal to maximum of mod of sigma 1 minus sigma 2 by 2, comma mod of sigma 2 by 2, comma mod sigma 1 by 2. On the plane of maximum normal stress, shear stress must be 0, but on plane of shear stress, normal stress need not be 0. Normal stress need not be 0. Normal stress on maximum shear stress plane. Put theta is equal to theta s1 or theta s2 in equation 1. Sigma theta, sigma average is equal to sigma x plus sigma y by 2 is equal to sigma 1 plus sigma 2 by 2. Diagram representation. Sigma x, sigma y, tau x, y, theta p in this plane, sigma 1, sigma 2. General element, find theta p by equating equation 2 is equal to 0, rotate by 45 degrees to get tau max and tau average. The summation of normal stress on any two mutually perpendicular planes remain constant. Sigma x plus sigma y by 2 is equal to sigma 1 plus sigma 2 is equal to sigma average plus sigma average. Sigma 110 degrees plus sigma 100 degrees is equal to sigma 35 degrees plus sigma 125 degrees. If shear stress is 0 on any plane, then plane can be directly considered as principal plane and those stresses as principal stresses. Sigma 1 is equal to sigma x, sigma 2 is equal to sigma 1 is not equal to sigma 2, sigma 2 is not equal to sigma x, and sigma y. This is one question. Maximum shear stress plane rotated by 40 degrees space. Sigma 1 is equal to plus p, sigma 2 is equal to minus p. Sigma, you have to get sigma xx, sigma yy, and tau xy from these things, which will be p, tau xy is p, and sigma x and sigma y are 0. General method to analyze the stress or Mohr circle method valid for 2D stress. Mohr circle is the locus of a point whose coordinates represent normal and shear stress on any plane. Important points. Every radial line at center of Mohr circle will represent an actual plane. Horizontal radial lines will represent principal planes while vertical radial lines will represent maximum shear stress plane. Every angle at center of Mohr circle will be twice that of actual angle in material. The center of Mohr circle will always lie on normal stress axis, that is x-axis. Construction of Mohr circle. Sign convention of shear stress clockwise positive, counterclockwise negative. And this is represented as sigma x comma minus tau xy as it is anti-clockwise. This is represented as sigma y comma tau xy. Steps: locate point A sigma x comma minus tau xy and B point B sigma y comma plus tau xy. Joint A and B with a straight join A and B with a straight line and it will represent diameter of Mohr circle. Wherever AB line cuts normal stress axis, it will represent the center of Mohr circle. Center of Mohr circle to the top is sigma average count on diameter d is equal to root of sigma x minus sigma y whole square plus 2 tau xy square. Radius is equal to d by 2 is equal to root of sigma x minus sigma y by 2 whole square plus tau xy square is equal to tau max is nothing but mod of sigma 1 minus sigma 2 by 2. Center is OE plus EC, which will finally get a sigma 1 plus sigma 2 by 2. Sigma is equal to sigma average. OD is equal to OE plus ED. OD, OD is equal to OE plus ED. So we will get sigma 1 is equal to sigma 2 plus 2 tau max. Sigma 1 is equal to sigma average plus tau max. Sigma 2 is equal to sigma average minus tau max. These are general workbook questions. Resultant stress by Mohr circle from origin root of sigma average square plus tau average square. Okay, mod sigma. Special cases of Mohr circle. 1D stress sigma 1 is equal to sigma 2 is equal to 0, tau max is equal to sigma by 2, sigma average is equal to sigma by 2. Pure shear 0, like just representation of Mohr circle. Only sigma acting. One point is 0, 0, the another point is sigma. This is 0 to A is minus 0 comma minus 2, 0 comma 2. The A and B are represented here and here, and by that we can draw circle. Sigma 1 is equal to plus 2, sigma 2 is equal to minus 2, sigma average is equal to 0, tau max is equal to tau. In case of pure shear, Mohr circle will be symmetric about both axes. In this case also Mohr circle will be symmetric about x-axis. Okay, beam of P is applied at a point on top of sigma tau sigma comma tau 0 comma minus tau. Okay, it will be a sigma comma tau 0 comma minus tau. Circle will be like this. Sigma 1 sigma 2 opposite nature in always on key. In case of beam we take in plane shear stress mod of sigma 1 minus sigma 2 by 2, as it will be tau max. Hydrostatic pressure sigma x is equal to minus p, sigma y is equal to minus p, tau xy is equal to 0. P is equal to pressure. A minus p comma 0, B minus p comma 0, which will be a point circle minus p comma 0, infinite principal plane. Sigma theta is equal to minus p, tau theta is equal to 0. Failure of materials. Brittle materials, compression, shear, tension, decreasing order of strength. Brittle materials are stronger in compression and shear and weaker in tension. Brittle material under tension fails at cross section like this. Brittle material with under compression fails due to maximum shear, crushing failure. It will be 45 degrees like this. Brittle due under torsion. Brittle under torsion again at 45 degrees, because the principal plane will be like that, and normal this straight line plane is maximum shear plane. As it is strong, it won't break in that direction. Ductile materials, tension, compression, shear is weak. Ductile material weaker in shear, stronger in tension and compression. Ductile material under tension at 45 degrees, cup and cone fracture. Torsion fails by at cross section maximum, as it is maximum shear plane. Strain analysis, replace sigma x by epsilon x, sigma y by epsilon y, sigma 1 by epsilon 1, sigma 2 by epsilon 2, tau xy by pi xy by 2. Only this is different one. Strain on inclined plane, epsilon theta is equal to epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2 cos 2 theta plus pi xy by 2 sin 2 theta. Pi theta is equal to minus of epsilon x minus epsilon y by 2 sin 2 theta plus pi xy by 2 cos 2 theta. Principal plane 2 tan 2 theta p is equal to 2 pi xy by 2 epsilon x minus epsilon y, tan 2 theta p is equal to pi xy by epsilon x minus epsilon y. According to the strain analysis, principal plane is a plane on which shear strain is 0. It means shear stress should also be 0 by Hooke's law. Therefore, principal plane located by stress and strain system is same only. Principal strains epsilon 1 comma 2 is equal to epsilon x plus epsilon y by 2 plus or minus root of epsilon x minus epsilon y by 2 whole square plus pi x y by 2 whole square. Maximum shear strain pi max absolute by 2 is equal to maximum of mod of epsilon 1 minus epsilon 1 by 2 epsilon 2 by 2 comma mod of epsilon 2 minus epsilon 3 by 2 comma mod of epsilon 3 minus epsilon 1 by 2. Pi max absolute is equal to maximum of mod of epsilon 1 minus epsilon 2, comma mod of epsilon 2 minus epsilon 3, comma mod of epsilon 3 minus epsilon 1. More circle for strain. Epsilon average is equal to epsilon x plus epsilon y by 2. Epsilon x plus epsilon y is equal to epsilon 1 plus epsilon 2 is equal to epsilon 10 degrees plus epsilon 100 degrees. Find out length of elongated diagonals. Okay, epsilon x6 is given, epsilon y, these are given. Epsilon theta, you can get theta which is 37 degrees. From that you can apply above formulas and we can get a dash b dash. Strain gauges, it is used to find normal strain when it is less than 0.001. Types of strain gauges: optical strain gauge, mechanical strain gauge, electrical strain gauge. These both work on magnification achieved, cheap and not much accurate concept. The change in length of wire is proportional to change in resistance. Capital R is equal to rho L by A. This is copper nickel alloy because of very high sensitivity. Strain lossette, it is combination of three strain gauges placed in three different directions in material. Note that measurement of shear strain is not practical because there is no such device available in market, but by the help of this arrangement we can make sure we can measure the shear strain based on arrangement of strain gauges. Following strain rosettes are available: rectangular, theta 1 is equal to 0 degrees, theta 2 is equal to 45 degrees, theta 3 is equal to 90 degrees. Delta strain gauge, theta 1 is equal to 0 degrees, theta 2 is equal to 120 degrees, theta 3 is equal to 60 degrees. Star strain gauge, theta is equal to theta 1 is equal to 0 degrees, theta 2 is equal to 120 degrees, theta 3 is equal to 40 degrees. Note steps. Note the readings of all the strain gauges. Epsilon theta is equal to epsilon x minus epsilon y by 2 plus epsilon x minus epsilon y by 2 cos 2 theta plus pi xy by 2 sin 2 theta. Example for rectangle, theta is equal to 0 degrees, epsilon 0 is equal to epsilon. After applying the formula, we will finally get epsilon 0 is equal to epsilon x. After epsilon 90 is equal to epsilon y. Theta is equal to 45 degrees, then gamma xy is equal to 2 epsilon 45 minus epsilon 10 minus epsilon 90. We can get epsilon x, epsilon y, and gamma xy. We can find everything. How many number of strain gauges are required to design state of plane strain? 3 strain gauges placed in 3 different directions in of the material. Step 3, epsilon 1 comma 2 is equal to epsilon x plus epsilon y by 2 plus or minus root of epsilon x minus epsilon y by 2 whole square plus gamma xy by 2 whole square. Step 4, epsilon 1 is equal to sigma 1 by e minus mu sigma 2 by e. Epsilon 2 is equal to sigma 2 by e minus mu sigma 1 by e. From this, sigma 1 is equal to e by 1 minus mu square into epsilon 1 plus mu epsilon 2. Sigma 2 is equal to e by 1 minus mu square into epsilon 2 plus mu epsilon 1. This is Lamb's equation. From this, we can find the sigma 1 principal stresses also. Okay, interesting. This is one workbook question. Determine principal stresses on the body. The data from above strain gauge, stretcher beam, will get everything like this. Okay, then determine stresses on body. Determine safety of material if allowable stress is 50 MPa. Epsilon x, epsilon y, gamma xy, we can get 2 epsilon 45 minus epsilon 0 minus epsilon 90. And epsilon 1 comma 2, we can get it like this. From this, sigma 1 is equal to e by 1 minus mu square into epsilon 1 plus mu epsilon 2. Sigma 1, sigma 2, we can get. As allowable, it is less than allowable, it is safe. In a stressed member, two strain gauges are fixed such that they are inclined at 30 degrees to known direction of principal stresses. The strain measured to these two strain gauges are 445 micron and minus 32 micron. is equal to 210 magnitude of principal stresses. Epsilon x, epsilon y given. Tan 2 theta p is equal to gamma xy by epsilon x minus epsilon y. And theta p, that they are inclined such that they are inclined at theta p is 30 degrees. So gamma xy you can get from that epsilon 1, epsilon 2 you can get from that sigma 1 and sigma 2 also you can get using the formula. A homogeneous isotropic material of size 20 into 20 into 20 is placed inside rigid box of internal diameter 20 into 20 into 20 centimeter cube. The top of box is open and material inside is subjected to a uniform compressive stress of 10 MPa from top. Assume no friction on side walls. Find out stresses on side faces of material. Also find out maximum shear stress, normal stress on the plane of maximum shear stress to changes in the volume of material given E is equal to 200 gigapascal. So from epsilon 2 is equal to minus mu sigma 1 by E, sigma 2 is equal to E epsilon 2. As material is not free to expand in x and y direction, epsilon x is equal to 0, epsilon y is equal to 0. Okay, from that we can get sigma. As there is no friction on side walls, so sigma 1 is equal to minus 10 MPa, sigma 2 is equal to minus 4, sigma 3 is equal to tau max is equal to maximum of mod of sigma 1 minus sigma 2 by 2 mod of sigma 3 minus sigma 2 by 2. From that we can get tau max, so sigma average is equal to mod of sigma 1 plus sigma 2 by 2. Epsilon v is equal to 1 minus 2 1 minus 2 mu by e into sigma x plus sigma y plus sigma z, which is nothing but delta v by v. Delta v is equal to minus 0.371 centimeter cube. Product of inertia. The moment of inertia about any two mutually perpendicular axes in the plane of area is called product of inertia. Ixy is equal to integral a xy dA. It may be positive, negative or zero depending upon position of axis with respect to given area. Among the two mutually perpendicular axes considered, if the body is symmetric about at least one of the axes, then the value of product of inertia is equal to 0. Ixy is equal to minus integral of minus xy dA plus xy dA is equal to 0. Ixy symmetry, then Ixy is equal to 0. Here about this axis Ixy is equal to 0. Here also about this axis Ixy is equal to 0. Principal moment of inertia, it is maximum or minimum moment of inertia about the principal axis. I1 comma 2 is equal to Ixx plus Iyy by 2 plus or minus root of Ixx minus Iyy by 2 whole square plus Ixy square. Principal axis, it is a combination of two mutually perpendicular axes about which product of inertia term will be 0. For this, one of the axis must be like this about which body is symmetry. Ixx is equal to I1 is equal to bdq by 12 major PMY axis. Iyy is equal to I2 is equal to dbq by 12 minor principal moment of inertia axis. Major principal moment of inertia axis plays important role while designing of beam. Minor principal MY axis plays important role while designing the columns. More circle Ixx, 0, Iyy, 0. Okay. Ixy, Ixx, Iyy, point circle A, B. The product of inertia is used to find out the principal moment of inertia for double symmetrical bending. Double symmetrical bending at the rate like Double symmetric bending, if P is applied like this at an angle theta, x, y, it is divided into the 4 coordinates 1, 2, 3, 4 at the rate of x section. My is equal to P cos theta into x. Neutral axis y 1 of 4 positive, 2, 3 negative. Mx is equal to P sin theta into x. Neutral axis x 1, 2 tensile positive, 3, 4 negative. Sigma A is equal to, in second plane, minus my by I into x plus plus mx by ix into y. But point A is at neutral axis. Sigma A is equal to 0. My by iy into x is equal to mx by ix into y. X by y is equal to tan theta is equal to mx by x into iy by my. A compressive load P is acting on cross section of column at h comma k. Find out the stress at point q x comma y. Sigma theta is equal to minus P by A minus Pxy by Ixx minus Ph into x by Iyy. H comma k is point which is perpendicular distance. From that we can get like sigma theta like this.